Hello friends. So the last part of photochemistry unit is today we are going to cover the last topic of this unit, that are solar cells. In the initial video we have already covered the two topics, that are prospects of solar energy conversion and storage, and the second one photoelectron chemistry. In case of photoelectron chemistry we have seen the photo decomposition of water, that is photolysis of water, and the decomposition of NaCl. In case of photo decomposition of water, or we may say the photolysis of water, there we have seen the semiconductor electrode. That semiconductor electrode is comes under the photogalvanic cells, where we have seen there is N-type titanium dioxide is being used as a semiconductor electrode, which is being placed in water, and then on the absorption of radiations, titanium oxide forms a electron hole pair, and then it forms hydrogen and oxygen at the respective electrodes. At titanium oxide there occurs the oxidation where oxygen is generated, while at the platinum electrode the hydrogen is being generated, which can be used in the fuel cells. We have already seen that is about the galvanic cells. So the first part will be photogalvanic cell, which we will be covering in this video, and the another one is photovoltaic cells. The photovoltaic cells are also called as the organic solar cells. Both these comes under photoelectrochemical cells or photoelectrochemical devices, where the photo means light energy will be converted to chemical energy, and then chemical energy will be converted to electrical energy. So it will be a three-step process. So as you can see here, this is pointer first. As you can see, this is the titanium oxide semiconductor electrode, where there occurs the oxidation by the liberation of electron as well as oxygen, and it is separated by some membrane, and here there is another metal storage electrode, which where occurs the reduction reaction and hydrogen is generated, as we have seen in the earlier video. And the next is photovoltaic cell. The part of photovoltaic is organic solar cell. So there are basically inorganic solar cell also and organic solar cell, but inorganic solar cell are having some limitation, that's why we have to focus on organic solar cells. So in this photovoltaic cells, there is a p-n junction type electrodes, and there occurs the potential difference between the two electrodes because of hole and electron pair, and that are called as excitons. These hole and electron pair are called as excited state electrons, are called as the excitons, and which gives the electrical energy. So such type of electrode will be there. We'll see it when. So the electrochemical devices which converts the light energy into electrical energy, as there occurs the conversion of light energy into electrical energy. It means it will be a charging process where light energy into chemical energy and then chemical energy into electrical energy. One will be the cyclical charging process and another will be the discharging process. So it will be similar to that of a battery. So on illumination, first the cell is charged. As we know, first the cell, when it is kept under light, then it will form the some chemical reaction, and the energy will be stored in the form of some chemicals, and then that stored chemical products energy can be utilized for the electrical purposes, that is the chemical energy can be converted into electrical energy. Now the light energy is converted into chemical energy by driving a suitable redox reaction against a potential gradient, and that redox reaction will be the reaction can be given as first acceptor species and another one is the donor species. Here A1 will get reduced and D2 will get oxidized, and this reaction is occurring in the presence of sunlight, or we can say the irradiation of light radiation. So this is the first process, which is called as charging process. While in dark, what happens that A2 becomes reduced while that of D1 gets oxidized. It means the reaction is being occurring A1 D1 D2 A2. The acceptor becomes the donor, donor becomes the acceptor. This type of redox reactions are occurring there. So the same things are being explained in this diagram, that is D1 converted to A1, and here A2 converted to D2. So this is the cell charging process. First, which is occurring in the presence of light, and another is cell discharge process, which is occurring in the dark. The reaction reverses spontaneously during the cell charging and discharging process, as we have seen, and there the chemical energy is converted to electrical energy, and the cell is discharged. So no chemical consumption is being occurring during the charge discharge cycle. So it is an ideal system, and it should be functional as a rechargeable battery without any loss of efficiency, and this is known as the photogalvanic cells, where the light energy is initially converted to chemical energy, and that chemical energy is converted to electrical energy. An example of that photogalvanic cell is a reaction of photobleaching of thionein by Fe2 plus ions. Thionein exists as a cation at low pH and can be represented as thionein plus. Overall reaction is TH plus twice Fe plus, it forms twice H plus. Let me take the pointer first. TH plus twice Fe plus twice H plus. In presence of light, it forms this 2H plus gets absorbed by the twice H plus and it forms TH3 plus, and this Fe gets what will say, it will lose one electron, that it will undergo oxidation and it will form the twice Fe3 plus ions. So this is our first part. First reaction is TH plus forming TH3 plus and Fe2 plus forming Fe3 plus. This is the cell charging process, and during discharging again Fe3 plus dissociate the two protons and forms again TH plus, while that of Fe3 plus take one of the electron from this proton which is coming from this species, and again it forms the twice Fe2 plus. That is as we have seen the reaction in the earlier one, which is A1 forming D1 and D2 forming A2. So such type of reaction is occurring here also. Now the sequence of reaction at the two electrode is, firstly we will see in here, that is at anode. The anode is absorbing some light radiation, and during that TH3 plus forming TH plus 2H plus 2 electron, and this is the charging process where TH3 is losing the 2 electron along with 2 protons, and while that of at cathode, what happens, the Fe3 plus accepts the electron coming from this here and it forms the Fe2 plus. This is the during in the dark, and it is called as the cell discharging process. The reactions which are occurring during that are, just you hold on this slide and hold on this point and just read that all the reactions which are occurring. Since this is the reaction, the main reaction will be TH plus twice Fe2 plus 2 protons forming TH3 plus twice Fe3 plus. This is the charging process which is occurring here on illumination of light radiation, while in dark the reverse reaction, which is twice Fe3 plus taking the 2 electrons and twice, and protons will get removed from the TH3 plus, and it is accepting the electron from here and forming the twice Fe2 plus and TH plus. This is the cell discharge process which is occurring at the cathode here, and the sequence of reactions are like this, as you can read it. Firstly, TH plus S0 plus, on absorption of some radiation, it will form the TH plus in the singlet first state. And then that singlet first state will combine with one proton first and form the TH2 2 plus, which is again in the triplet state. That triplet first state TH2 plus combined with the Fe2 plus, and it will form the twice TH2 plus plus Fe3 plus. Here your Fe is being getting reduced. Sorry, it is losing one electron. Loss of electron, oxidation. It is undergoing oxidation. It is undergoing reduction. We can see that. So it is the second. It is the same. Then that twice TH2 plus species. It is forming TH plus plus TH3 plus species. That TH3 plus plus Fe3 plus. It is forming. It will lose one proton and form the TH2 plus plus Fe2 plus plus protons. That TH2 plus again, it is forming TH plus plus protons plus electron. That Fe3 plus plus electron forming Fe2 plus, and TH2 plus plus Fe3 plus, it is forming the TH plus plus H plus plus Fe2 plus. That TH plus S1 is the singlet state of dication, and T1 it means the triplet state of protonated di, and TH2 plus semi-thionine half reduced radical ion, and TH3 plus leucothionine. So these are the reactions. Just practice it once, you can learn it. Now the efficiency. Efficiency of photogalvanic devices for solar energy conversion is not very good. It is because of two factors, that are difficulty in preventing the spontaneous back recombination reaction. As you can see, the cell charging and discharging may occur get together, and furthermore we cannot utilize the total solar spectrum. Now photovoltaic cells. Photovoltaic cells, these are the generation, as it is having, as the photogalvanic cells are having some difficulties, or we may say disadvantages. So to take over that, the another cell is photovoltaic cell. So in case of photovoltaic cells, as the name suggests, Voltaic means difference in voltage. It is a basically two types of semiconductors will be there, N type and P type. So it is a PN junction diode type. So the generation of voltage across the PN junction in a semiconductor due to absorption of light radiation is called photovoltaic effect, and the devices based on this effect is called as the photovoltaic effect. The voltage, generation of voltage across the PN junction in a semiconductor due to absorption of light radiation is called photovoltaic effect, and the devices based on the effect is called as the photovoltaic devices, as you can see in the diagram. It will absorb some light radiation, there will be the generation of voltage, and which will be utilized for the generation of electrical energy. So simple, from this diagram you can define it. Now in order to take over the disadvantages of photogalvanic cell, the next cells are photovoltaic cells. In photovoltaic cells, silicon solar cells, they are found to be the most efficient quantum conversion devices. Silicon solar cells, these are the inorganic solar cells. So here the light energy is directly converted into electrical energy without the intermediate chemical reaction. That is, in galvanic cells, what is happening initially? Photogalvanic cell, initially the light energy is converted to chemical energy, and that chemical energy will then converted to electrical energy. But in case of photovoltaic, what happens? The basic difference is light energy is directly converted to electrical energy without the intermediate chemical reaction. So just remember the difference between the two. And the photocurrent is used to charge a storage battery. Since silicon, now there are some disadvantages of silicon solar cells, because silicon of very high purity is required and they are fairly expensive. And another one is they are light stability and range of absorptivity. Redox systems might be more, they are more useful because of some factors like they are light stable towards light, they have high range of absorptivity, and their redox systems, because of which they are being more interesting. So the photo-induced electron transfer in aqueous solution of tris 2,2-bipyridine ruthenium has been found to decompose water into a mixture of H2 and O2. Here in photovoltaic, I have taken some more content. You can just shorten it while after reading the video, after watching the video. Just take as much as you want. I will tell you what much is important. So this complex that is tris 2,2 bipyridine ruthenium complex. It can serve both as an electron donor as well as electron acceptor in the excited state. So the efficiency is low because of the barrier to electron transfer. And in order to remove that electron barrier, when a spread, that is when that complex is being spread as a monolayer on a glass slide after attaching to a surfactant chain, visible evolution of gases occurs when a battery of about 20 to 30 slides are exposed to sunlight. Many reducing cations in aqueous solutions can photoreduce water in low yields and when irradiated in their charge transfer bands. Similarly, oxidizing cations can photooxidize water. That is, reducing cations can photoreduce water and oxidizing cations can photooxidize the water. For example, several hydride complexes of transition metals such as cobalt decompose on irradiation to yield the molecular hydrogen, and the complexes with electron withdrawing ligands on the other hand can decompose water spontaneously. So this may be the complex where COL4 in presence of water decompose the water by forming the hydride complex with the elimination of oxygen. If suitable system of ligands could be found such that light reaction is endergonic and dark reaction is exergonic, then the net result will be decomposition of water, as we have seen. So for that, a biological fixation of CO2 and water to reduce compounds which can be used as fuels will be a reaction of immense use. Until now, this has been very useful. And the simplest of these compounds are formic acid, formaldehyde, methanol and methane. So all of these where water and CO2 can combine to form the formic acid, formaldehyde, methanol, methane and giving you this much energy. All these reactions are highly endothermic. The products of these reactions also have high calorific value. Fuels, they can be used as fuels. Next, in nature, fixation of CO2 is a dark process, although initiated by light-induced chain of reactions, as we have seen the CO2 fixation process. Except in some special plants like rubber, CO2 is still not completely reduced. Carbohydrates are the common stored products and rubber plants produce hydrocarbons. Now, a hypothetical photoelectrochemical cell based on membrane model photosynthesis has been given here. What I am telling earlier, that one is not much important regarding in exam point of view. So just go through that for clearing the concept. So in case of photoelectrochemical cell, it is a hypothetical photoelectrochemical cell where it is based on the photosynthetic model. Just as the photosynthesis occur in case of plants, the same theme is used here. For that, they have used the barriers. This is some middle portion and we will get the electricity. For that, these are called the phospholipid layers. Then this layer is called as the electron carrier, beta carotene, and these are the sensor parts. So the membrane, this membrane, phospholipid layer, electron carrier, and then the sensitizer. The membrane gives unidirectionality to electron flow and prevents the spontaneous and direct recombination of photogenerated species. That means it will reduce the reverse reaction. You can get the reaction in one direction. Then the recombination occurs through external circuit only, converting light energy into electrical energy. But remember, it is a hypothetical cell. So these kinds of totally synthetic systems which emulate and stimulate nature may very well in nature in near future provide alternative sources of energy. Means this is the work which should be done by you. Think on it and try for it. Now, organic solar cell. It is also a part of photovoltaic cells. One of the example of photovoltaic cell is the organic solar cell, where light energy will be directly converted into electrical energy without any chemical reaction in between, without any chemical composition in between. So, it consists of three parts. First is PET foil, then ITO, then PEDOT. This is some fullerene material, and this is the aluminium. So first is your this electrode aluminium, and PET foil is the another electrode, and this is some intermediates. Now schematics of plastic solar cell. PET means polyethylene terephthalate. ITO indium tin oxide. PEDOT PSS poly 3,4 ethylene dioxythiophene, and the active layer, which is this layer, it is the fullerene blend, and last this is the aluminium. Now, an organic solar cell or plastic solar cell is a type of photovoltaic that uses organic electronics. It is a branch of electronics which deals with conducting organic polymers or small organic molecules for conversion of sunlight into electricity by photovoltaic effect. So most organic photovoltaic cells are the polymer solar cells. The molecules used in organic solar cells are solution processable at high throughput and are very cheap, resulting in low production cost to fabricate large volume. Combined with the flexibility of organic molecules, they are cost effective for photovoltaic applications as they are very cheap. Then the molecular engineering can change the band gap, allowing for the electronic tunability. As you go on changing the functional groups of polymers, they will change the band gap and you can tune the electronic frequency. The optical absorption coefficient of organic molecule is also very high. So you can large amount of light can be absorbed with a small amount of materials, usually of the order of hundreds of nanometers. As the optical absorption coefficient is very high, large amount of light can be absorbed. The main disadvantage associated with organic photovoltaic cells are they have low efficiency, low stability, low strength compared to that of the inorganic photovoltaic cells, which are the silicon solar cells. Now the advantages of polymer solar cells. Also as they are having such disadvantages like low efficiency, low stability, low strength, but they are having still some advantages over that of the silicon based solar cells, which are they are lightweight first, so they can be used for sensors. Then they're potentially disposable, which is the main part. What we create, it should must be disposed very safely to environment. It should not affect the environment adversely, and inexpensive to fabricate. They are flexible, customizable on the molecular level, and potentially have less adverse environmental effect, which is the most important part. Then polymer solar cells also have potential to exhibit transparency. They're also transparency, so they can be used in windows, walls, flexible electronics, etc. An example of this device is shown here in figure, which is this one. You can place it in your window, and if the light energy is coming on your window, it may automatically get converted into the electrical energy, because conversion of light energy into electricity is a part of this cell, that is a photovoltaic cell. The disadvantage of polymer solar cell are their efficiency. They are having only 1/3 of efficiency of the hard materials which are being used, and they experience the substantial photochemical degradation. The polymer solar cells inefficiency and stability problems. They can be combined with the promise of low cost and increased efficiency. It means the polymer solar cells, although they are having inefficient and their stability problems as they are undergoing the photochemical degradation, they can be solved with their low cost and increased efficiency, and which made them popular in the solar cell research. In 2015, the polymer solar cells were able to achieve only 10% efficiency via tandem structure, while in 2018 it comes to 17.3. Now, there are different types of organic solar cells which are single layer, bilayer, discontinuous layer, continuous layer. You can read it from Google search. Just in exam they ask you about the bilayer, so we will focus on that bilayer. Here, in case of single layer, it will be such type of electrode 1, electrode 2, and the organic electronic material. It means between the two electrodes there is only single layer. Depending on the layers, there will be different types of organic solar cells. Single layer organic photovoltaic cells are the simplest form, which is shown in this figure. Separation by one layer. These cells are made by sandwiching a layer of organic electronic materials between two metallic conductors. Typically a layer of indium tin oxide, that is ITO, which is the electrode 1, and the layer of low work function metals such as aluminum, magnesium or caesium. The basic structure of such a cell is illustrated in figure, as you can see. Now, the difference of work function between the two conductors, that is this electrode 1 and electrode 2, sets up an electric field in the organic layer. When the organic layer absorbs light, electron will be excited to the lowest unoccupied molecular orbital. That is, upon the absorption of light, the electrons from the highest occupied molecular orbital will be transferred to the lowest unoccupied molecular orbital, creating a hole there, and thereby this electron hole pair is called as the exciton, and there occurs some Coulombic interactions or Coulombic electrostatic attraction between the two. The potential created by the different work functions helps to split the excitons pairs, pulling electrons to the positive electrode and holes to the negative electrode. Examples of single layer organic solar cells are firstly the pair aluminium silver, aluminum first electrode, silver electrode 2, and magnesium phthalocyanine pair will be the intermediate layer. So this will be the first type of cell which may be there, which is having the efficiency of 0.01%. The another one is the conjugated polymers were also used in this type of photovoltaic cells. One device used photoacetylene as the organic layer with aluminum and graphite. Means here it will be aluminum, it will be graphite, and in between there will be the polyacetylene producing an open voltage, and it will have the efficiency of 0.3%. Next one is aluminum and platinum. Here it will be aluminum, it will be platinum, and in between this it is a poly-3-methyl-thiophene, and it is having the efficiency of 0.17%. Then the given here is ITO, aluminum, and PPV layer in between this. They are known to have the efficiency of 0.1% under white light illumination. Now, bilayer cells. Bilayer cells contain two layers in between the conducting electrodes. As you can see, it is same. The electrode 1 ITO metal, electrode 2 might be aluminum, magnesium, calcium metal, and in between this it is the electron donor and electron acceptor pair. So there are basically two layers. The two layers have different electron affinity and ionization energies, and therefore the electrostatic forces are generated at the interface between the two layers. As they are having different electron affinity as well as different ionization energy, there will be the generation of electrostatic force. It means there will be the difference in EMFs, which will helps in creating the electricity. So light must create the excitons in this small charged region for an efficient charge separation and collecting. The material are chosen to make the differences large enough that these local electric fields are strong, which splits the excitons much more efficiently than the single layer photovoltaic cells. And the layer with higher electron affinity and ionization potential is the electron acceptor pair. As here it is electron acceptor, it is having the higher IP as well as higher electron affinity. And this structure is also called as the planar donor acceptor heterojunction. Donor acceptor heterojunction. The examples of bilayer solar cells will be based on this electron 1, electrode 2. These will be the same, and this electron donor and electron acceptor species will be changing, and based as they changes, the name of the cell changes and the efficiency changes. So first one is C60. C60 has high electron affinity, and a C60 MHPPV double layer cell has a relatively high fill factor of 0.48 and it has an efficiency of 0.04%. A PPV C60 cells displayed a monochromatic external quantum efficiency of 9%, a power conversion efficiency of 1% and a fill factor of 0.48. If the copper phthalocyanine is being used as the electron donor and perylene tetracarboxylic as the electron acceptor, then the efficiency changes to 1% and a fill factor is high as 0.65. Then Halls and others use the layer of bis ethylmidoperylene. That is, he used a layer of bis ethylmidoperylene over a layer of PPV as the electron donor. It is the PPV is the electron acceptor and the electron donor is bis-phenylmidoperylene over a layer of PPV as the electron donor. So PPV is electron acceptor and this one is the electron donor here, this much complicated name. So this cell has a peak external quantum efficiency of 6% and power conversion efficiency of 1% and a fill factor of 0.6. The issues comes like that the diffusion length of excitons in organic electronic materials is typically on the order of 10 nanometer. In order for most excitons to diffuse to the interface of layers and split into carriers, the layer thickness should be in the same range as that of the diffusion length. However, polymer layer typically needs a thickness of at least 100 nanometer to absorb enough light. At such a large thickness, only a small fraction of the exciton can reach to the heterojunction. Main issue lies in the diffusion length. The diffusion length should be in the same range which is being required for the excitons movement. So that one is the issue. Thank you. I hope you got the topic. Just go through Google also and know more about the organic solar cell, and this much is sufficient for you for your exam point of view. Thank you. A mind that is focused can overcome the biggest challenges. This question which was asked an exam on this topic is give what are organic solar cell and what is bi-layer organic solar cell. So you can first do the diagram, then example and how it works and its efficiency. That much is sufficient. Thank you.